Very good morning to everyone. I am pleased to introduce Dr. Samit Gupta, an associate professor at the Department of Theoretical Physics, Tata Institute of Fundamental Research, Mumbai. Professor Gupta is a distinguished theoretical physicist specializing in nonlinear dynamics and statistical physics. He earned his PhD from Tata Institute of Fundamental Research under the supervision of Professor Masansar Burma in 2008, and he pursued postdoctoral research at leading international institutions, including the Weizmann Institute of Science, Israel, Jens Line, France, University of Paris at France, and Max Planck Institute in Tersen, Germany. His research focuses on collective dynamics, long-range interacting systems, and phase transition in nonlinear systems. With these few words, let me invite him to deliver his talk. Thank you, sir.
Okay, so let me start by thanking the organizers, especially Professor Lecture1 for this kind invitation. I sincerely regret that because of some issues at my end, I am unable to travel and give the lectures in person. I would have very much liked to be there and to give the lectures in person. Unfortunately, that could not happen, and I'm very sorry about it. So to compensate for that, what I will do is that, of course, all my lectures are written up. So I will share with you the lecture notes and also the lectures that I'm giving now, that I will be giving over the next 4 days, 3 days and today. They will all get recorded. So at some point, we will share with you the videos of the lecture, so you can view them later. Okay, so that is that. And yeah, so especially to the participants. Okay, so before I start, let me get an idea of who the participants are. So could you please confirm, like, are most of you college teachers, or a significant fraction of you are master students? I mean, can somebody just summarize for me, like, you are largely college teachers or largely master students?
Sir, PG and research scholars and faculty.
Oh, PhD research scholars and faculties. Okay.
Faculty and MSc students also, sir.
MSc students also. Okay. Okay, so that's fine. So please do feel free to, stop me if at some point you feel something is not clear and so on. So just stop me, without any hesitation, without any fear or anything. And of course, you don't need to fear me, because anyways, I'm not there in person. So therefore, anything that happens will happen only virtually, and nothing will happen, that I can assure you. So please do stop me if you find something is unclear or something you need, you require me to repeat and so on. So yeah, okay. So the plan is the following. So what I'll do is that, so let me just start. So this is the plan basically. So this is, this font size is okay? Or shall I write big? Bigger than?
Yes, sir, this comes okay, sir.
Okay, and the chalk color is okay, or shall I use this one? Which one? This or this?
Second one, sir. Second one. Second one, sir.
Second one. Okay, fine. Okay. So the plan is the following. So what I will do is that today I will do largely a review of thermodynamics. Thermodynamics. And I don't think today I will have time to go to StatMech, and then for the remaining 3 days I will talk about StatMech, largely classical, and perhaps one lecture on quantum. So that's roughly the plan. Okay. Now, perhaps I should mention some standard references that I typically, refer to while teaching these courses, and I think the teachers may find them useful, and also the research scholars also would find them useful. So for thermodynamics, I would strongly recommend that you read a book by Enrico Fermi. So the book is called Thermodynamics. Okay, so this is the Nobel laureate Italian physicist Enrico Fermi, Fermi-Dirac statistics, etc. So that book is very good for thermodynamics, and it is written almost at the level of a storybook. I mean, it is so well written that once you start reading it, you won't stop. You won't put it down until you have finished reading the book. So that is one. And for StatMake, my standard reference is the book by Carson Wong. It's a very old book, but the book, this is the book from which I think generations of students have learned statistical mechanics. So I strongly recommend that you read this one. Also, together with my former PhD student, we have written a book. Let me just write down the reference. It's called Physics of Noise. And the authors are my PhD student Devras and myself. And it's published from Springer 2024, last year. So you can look up that book also. That book, my lectures will be largely based on the material that's presented in this. Okay, are there questions? You have some questions on the references and so on, or shall I move on? Hello? Hello?
Sir, no questions, sir.
No question. Okay, thank you. Okay, so let me start with thermodynamics. Okay, so I'll start with this one. So please do stop me. Please do be interactive, because if you just sit there and not interact, then it would not help. Okay, because we are here. We all are here to learn something. So if you just sit silent and just take down notes and go back, then it will not help anyone. Okay, so please do speak up. Okay, nobody will kill you. Nobody will do anything. So therefore, please do speak up. Okay. So I will start with the review of thermodynamics.
Samir, can you hear me?
Yeah. Hello.
Hi, Arul here.
Huh.
Samir, you're actually facing not the camera. You're facing, I think, us in your thing. So you have to turn. Now you're facing us. Okay, good.
Oh, okay, fine. So when I have to say something, I have to do like this.
Yeah,
Okay, I understand.
Okay,
fine.
And I think they need a mic for them to hear you. Okay, so any interruption, any questions, we'll have to go through the mic, correct? Yeah. Okay. Yeah, please go on. Thanks. And I think the upper part of your board appears rather white. Is that because of some glare, or is that because of light, or is that something?
Okay, so what I'll do is that let me not write anything in the upper part. Okay,
Yeah,
it is because of some glare.
Yeah, glare is there. So maybe the bottom half of the board is good.
Yeah, so I just drew a line here, so I'll write below this one.
Yeah. Okay.
Okay.
Thanks. Please go ahead.
Okay, so let me start with this review of thermodynamics. So, before starting with the review of thermodynamics, let me just spend some time on explaining why do you need to study statistical mechanics. I mean, why there is this subject called statistical mechanics. Okay, so let's first recall classical mechanics. Okay. So in classical mechanics, typically what you do is you deal with a collection of particles, let's say. Okay, so there is some collection of particles which are described by some Hamiltonian, which is a function of all the coordinates and all the momentum. Let's say I'm in 3 dimensions, so therefore Qi is at the coordinates and Pi is at the conjugate momentum, and let's say I runs from 1 to n. Okay, so there are n particles. Okay. So in classical mechanics, of course, you know how these particles are going to move in time. These are given by the Hamilton equations of motion. Qi dot is equal to del H del Pi. This is one. And the second equation is Pi dot minus del H del Qi. So this is the formulation of classical mechanics. And then of course you can go on to, study things like constants of motion, this, that, integrals of motion, this, that, etc. But in classical mechanics, within this framework, there is nothing that tells me, or there is no prescription for answering a very simple question. That is the following, that why the color of this chalk is white. Okay. So this chalk, I can think of this chalk as composed of very many particles, okay? And in fact, I know that in 1 mole of this chalk, there's going to be 10 to the power 23 constituent atoms or molecules. So these things are known to me, but what I don't know is that I know how these individual particles making up this chalk, they move, but then I don't know how does that fact help me to explain the fact that this chalk is white in color. It is white in color and it is hard and so on. So these are properties which are known as macroscopic properties, macroscopic or observable properties. Observable means properties that you can observe with your eyes. I can, observe with my eyes that the chalk is white in color. I can feel that it is hard and so on. But these are properties that I can observe and yet I am unable to explain on the basis of this formulation of classical mechanics. Okay? So observable properties. What does macroscopic mean? Macroscopic means the following, that the chalk being white in color and the chalk being hard and so on. These are properties that refer to the full collection of atoms and molecules. There is no point in saying that the 5th atom making up the chalk is white in color. Okay? So these properties, they don't refer to the individual constituent atoms or molecules. They refer to the whole collection. The collection as a whole has got certain properties, white in color or hard and so on. Okay? So therefore, in classical mechanics, there is no prescription that tells me, or there is no formula that tells me that, for example, color of chalk. Okay? So there is no such formula that tells me that, okay, what you have to do is that you have to take the momentum variables and perhaps, raise it to the power 56 or something. So this kind of prescription is not there. So I do not know how to explain the chalk color being white on the basis of the information that I have about the coordinates and the momenta of the particles making up the chalk. So this is a lacuna of classical mechanics. So classical mechanics doesn't deal with macroscopic properties. There is a better name for it, but even if you don't understand it, it's fine. These are called emergent properties, properties that emerge. Okay, so you have many collections. So you can think of these emergent properties as emerging also in let's say in human society. Okay, so there is a very interesting quotation that man is kind, but men are cruel. That as individuals we are typically very kind people, but when a collection of us, let's say several humans, we get together and then we gossip and then we start discussing and so on, and then we may come up with some collective opinion about someone. We may say that, look, this guy is not good, I don't like him and so on. But individually, perhaps we don't dislike him as much as we dislike him when we are talking about him collectively. So these are known as emergent properties. And in classical mechanics, there is no formulation, there is no prescription to understand how emergent properties, how they emerge from interactions and so on. So this is a problem of classical mechanics. The problem is, it still persists if you go to a quantum mechanical description. In the quantum mechanical description, what you have is, instead of the coordinates and the momenta, you still have the Hamiltonian. Of course, now it becomes an operator. And instead of the coordinates and the momenta, you now have a wave vector or a wave function, which will be a function of course, all the coordinates making up the system. And the prescription is that you say that I h bar del psi del t is equal to h psi. Okay, so this is just these two prescriptions, they can be thought of as same footing in the sense that in the classical mechanical setting you have the Hamilton equations of motion, or more precisely the Newton's equations of motion. In the quantum mechanical case, you have the Schrodinger equation, but none of these prescriptions can tell you how to explain this very simple fact that the chalk is white in color. Okay? So therefore, we need to go beyond this classical and quantum mechanical description of matter, and we have to come up with a new framework that would allow me to explain why chalk is white in color, why a collection of people could be cruel, why, let's say, like another very, very beautiful example of emergent property is the emotions. Like we, as humans, we are made up of cells and tissues. We know from our biology course that we are made up of cells and tissues. Now, as humans, we have certain emotions. For example, we may get sad, we may get angry, we may get, whatever, like jealous and so on. We may envy someone. But these are properties at the macroscopic level, because at the level of cells and tissues, there is no point saying that the cell number 5 has become jealous of cell number 7. No such thing happens at the cellular level, but at the at the level of at the macroscopic level, you have certain emergent properties. Humans can be jealous, can be cruel, can be happy, can be sad, and so on. Okay. So therefore, we need to go beyond the classical and quantum mechanical description of matter and come up with something that would allow me to explain these collective properties, these emergent properties or macroscopic observable properties. Okay. Are there any questions up till now? So shall I take it that silence means you don't have any question? Shall I take it like that?
Yes, sir.
Okay, fine. So, how did the subject of statistical mechanics develop historically? So the way it developed is that people understood that classical mechanics is inadequate in explain these macroscopic properties. So therefore, people started doing experiments. That in those days people had the with the advent of industrial revolution, they had the recourse to do experiments with gas. Okay, so they had a typical experimental setup would be that you take some container, some cylinder, which has a piston that you can pull out or push it in, and there's some gas contained here, and they started doing experiments with such a setup in order to gain some insights, okay, as to how collective or like emergent properties behave and so on. Okay, and they came up with, for example, for an ideal gas, they came up with this experimental fact that PV is equal to N kBT and so on. This, I guess, P is the pressure, V is the volume, N is the number of gas atoms or molecules, whatever. Kb is the Boltzmann constant, and T is the temperature. So this is an experimental fact. And people kept doing experiments, and on the basis of these experiments, they came up with certain laws of nature. Okay? So it's a subject that's not there within the framework of classical mechanics. In classical mechanics, we have the you can continue. So in classical mechanics, you have the Newton's laws of motion, the three Newton's laws of motion. But then beyond classical mechanics, they found while experimenting with gas that you may also have laws which apply to a whole class of systems, and these are the thermodynamic laws. Okay, these are not captured by the three Newton's laws of motion. These laws go beyond the Newton's laws of motion, and they are called the thermodynamic laws. So there's the first law of thermodynamics and the second law of thermodynamics, and these laws apply as opposed to Newton's equations of motion. These laws apply to a macroscopic collection of atoms and molecules. So let's say to this chalk, if I have to apply the thermodynamic law, then I am very good. But if I have to apply the thermodynamic law to the fifth atom making up this chalk, then I'm not doing a good job, because the thermodynamic laws apply to a collection of atoms and molecules, namely to macroscopic properties. Okay. So to do that, let me, as I had told you, as a plan, what I'll do is that today I'll do a review of thermodynamics. What are these thermodynamic laws? And in order to do that, I need to define certain, So in order to do that, I need to define certain quantities which were not defined within the framework of classical mechanics. So therefore, we have to go beyond classical mechanics and define these quantities. So let's do that. Okay, so the first one is, as I mentioned, so thermodynamics is a phenomenological theory. Okay? Phenomenological theory. What does it mean? It means that in thermodynamics we will encounter laws, but these are only laws. These are not theorems. You cannot ask what is the proof of second law of thermodynamics. Can I have a mathematical proof of second law of thermodynamics? No, you cannot have. How these laws came into existence? Well, they came into existence on the basis of experiments. People did experiments with a whole lot of setups, and they found that in every experiment that they performed, certain things are true, certain things hold good for every experiment that they do, and therefore they started thinking that perhaps there are certain laws that nature follows. These are laws of nature. Okay, these are laws that are followed in every experiment that they did and that they do even today. So that means that thermodynamics, it's a phenomenological theory. That is, you observe a phenomenon, not just in one setup, but across a whole bunch of setups, and then you come up with certain unifying principles. You come up with certain laws that you feel are applicable to every experimental setup you deal with. Okay, so therefore, this thermodynamics, it is based. I think it is important to emphasize this fact that it is based entirely on experimental observation. Just as Newton's laws of motion are based on experimental facts. You cannot say, what is the proof? Can you give me a mathematical proof of Newton's third law of motion? No, there is no mathematical proof, because it's a law as opposed to a theorem. Okay? I hope you know the difference between a law and a theorem. A theorem is a mathematical statement that has a rigorous proof based on certain assumptions. As opposed to a theorem, a law is something that you find applicable to a whole lot of experiments that you do, and you seem to think that perhaps nature follows certain underlying laws and so on. Okay? So there is a mathematical proof of a law. So the thermodynamics, it is based entirely on experiments. That is one fact. Secondly, thermodynamics, it applies to, as I was mentioning, it applies to a macroscopic system. Macroscopic, or a better word is thermodynamic system. What does it mean? I will explain in a minute. Thermodynamic system. What does it mean? It means a collection of atoms and molecules, but the number of atoms and molecules is of the order of 10 to the power 23, the Avogadro number. Now you may think that, oh my goodness, I have to deal with so many atoms and molecules. Where do I get so many atoms and molecules? You don't have to worry, because in every 1 mole of a substance, you have that many atoms and molecules, and 1 mole is atomic weight in gram. So therefore, you are in good shape. You don't have to, deal with, 1,000 kilogram of carbon to have that many atoms and molecules. Only 1 mole of it will contain that many atoms and molecules. So the number has to be really very large. Thermodynamics does not apply to 1 or 2 atoms. Suppose you give me a collection of 7 atoms and ask me to apply the laws of thermodynamics. No, they won't apply. Okay? So they would apply only to a large collection of atoms and molecules. That's the first thing. The second thing is the volume. These are atoms and molecules, they're contained in a volume, okay? So that volume has to be much larger than the atomic volume. So the atomic volume will be what? Let's say, let's say if I think of the hydrogen atom and so on. So let's say it will be very small, let's say 10 to the power by angstrom, let's say angstrom cube. That would be the scale. So therefore, we will be dealing with things which are at the level of, this volume, it's of the order of, let's say, centimeter cube and so on, millimeter cube, not at the level of angstrom cube or nanometer cube, then thermodynamics will not apply. Okay? So this is the second thing. Then the third thing is, thermodynamics deals with time independent So let me explain what do I mean by that. So macroscopic properties I already explained. Okay, a simple way to remember what a macroscopic property is to say that a macroscopic property is something that I can see with my eyes, that I can measure in an experiment. Okay, so these are properties that I can see with my eyes, as simply put as that. Okay. And what does time independent mean? Time independent means what it means, namely that thermodynamics deals with properties that are time independent. For example, the color of this chalk is white and it will continue to remain white. So that particular part of the dynamics, when things become time independent, okay, for example, what is the part of the dynamics when it does not remain time independent is when you are growing this chalk. Okay, when you are growing this chalk from whatever the chemical process is, there things are changing. But once you have found this chalk and this chalk has got a particular color that is white and the color is not changing as a function of time, this is the domain in which I will apply thermodynamic laws. Okay? Can you tell me one property of this chalk which will not remain time independent as I go along? One property of this chalk that will not remain time independent as I go along. It would continue to remain white in color, but there is a macroscopic property. It's a macroscopic property, but this macroscopic property will change as I go along in this lecture. What is that property? No, come on. I mean, it cannot be that none of you can come up with an answer. What is that macroscopic property that will change as I go along in this lecture?
Volume, sir.
Yeah, or more precisely, the length of the chalk. Okay, surely the length will decrease. Okay, because it will reduce in time because as I'm using the chalk, yeah, length and volume. Okay, they are the same. Very good, good, good. Okay, so if I am to apply thermodynamics to describe the length or the volume of this chalk, then I will not be doing a good job, because thermodynamics deals with time independent properties. So there is a name for these time independent properties. So this instead of writing such a big word, you just write equilibrium property. So thermodynamics deals with a thermodynamic system, equilibrium properties, macroscopic properties. So until now, we have learned three keywords, okay? Thermodynamic system, macroscopic properties, time independent macroscopic properties. Okay. Okay. Here. We will deal with, let's say, in this set of lectures, we will deal with a very specific thermodynamic system, which is a gas. Okay. Now, why do I deal with gas? Because historically, that's how thermodynamics and statistical mechanics develop. And so, therefore, it is easy to understand the concepts if we take the example of gas. But that doesn't mean in any way that thermodynamics applies only to gas. Thermodynamics, in fact, applies to a DNA. Statistical mechanics also applies to a DNA. From DNA to black hole, at every level, whenever you have a collection of very many objects interacting with one another, you can safely apply thermodynamics. The only thing that you need to know or need to keep in mind is that that collection has to contain a large number of constituent elements, not just one or two. Okay? But we will deal with a gas system because that is, as I mentioned, historically, that is the framework in which statistical mechanics and thermodynamics were developed. Okay? So the system that we will deal with is a fluid system, let's say more precisely. And for a fluid system, what are the observable macroscopic properties? This we know from everyday experience. The observable macroscopic properties are the pressure, the volume, and the temperature. Just to fix our ideas, you can think of a gas which is contained in a cylinder, and there is a piston that moves in and out. And you may ask, what is the total pressure exerted by the gas on the walls of the cylinder? What is the volume occupied by the gas? And what is the temperature of the gas? These are very natural variables if you are talking about a gaseous system. Okay. Now it turns out that let me move again this part. So when the system is in equilibrium, the system is yeah. When the system is in equilibrium, namely this gas contained in a cylinder and there is a piston that moves in and out. And when the system is in equilibrium, that is, when you measure the value of the pressure, the volume, and the temperature, and you find that they are time independent, there is a relationship between these three quantities. They cannot all be independent of one another in equilibrium. Okay. So what is the relationship between them? So that relationship goes under the name of equation of state. For example, for an ideal gas, I know how does this equation of state look like. It looks like PV is equal to NKV. So therefore, for an ideal gas, we see that when the ideal gas is in equilibrium, pressure and volume and temperature, they are not independent of one another. They are dependent on one another through this equation of state. So therefore, whenever you have a macroscopic system which is in equilibrium and you measure the macroscopic properties of the system, you find that there is a relationship between the different macroscopic properties of the system, and you call that the equation of state, of which one example is the ideal gas. Okay? Of course, if you are not dealing with an ideal gas, you will get a different equation. But for every substance, there is such a thing as an equation of state. What is the next thing that we should know is the concept of thermodynamic transformation. Thermodynamic transformation. What does it mean? It means the following. Let us look at this example. The piston is immobile. You have kept it stationary at one point. You measure the pressure, you measure the volume, you measure the temperature. And let's say if the gas is an ideal gas, you find that PV is equal to NKV. The system is in equilibrium, everyone is fine and everyone is happy. Now what happens is that since this piston can be pulled out or pushed in, suppose I start pulling out the piston. Okay? So therefore the system is initially in equilibrium, and as soon as I start pulling out the piston, I will be disturbing the equilibrium state of the system. The system will no longer remain in equilibrium. Okay? And so what I will do is that I will say that the system is undergoing a transformation. The word transformation has got the same meaning, same connotation as the one that you have for this word in English. Okay, so connotation is the following, or the meaning is the following, that you are changing the state of the system. Okay, and how you are changing? Initially, the system was in equilibrium, and then you are pulling out the piston and you are changing the equilibrium state of the system. So that's called the thermodynamic transformation. Now, transformation can be of very different types, and one particular type is of great relevance in thermodynamics, which is the following, that initially the system is in equilibrium, and now when you start pulling out the piston, you pull it out so slowly that the system, of course, is no longer in equilibrium, but it gets to a new state which is almost in equilibrium. Okay, so that is to say, you start with the system in a state which is in equilibrium, and then you start pulling out the piston. This is in some imaginary space. Okay, so what I do is that I denote the state of the system by this dot. Initially, the system is in equilibrium, and then I start pulling out the piston very slowly. And if I do so, then the system will jump from this equilibrium state to a state which is almost in equilibrium. And if I keep pulling out the piston, then the system will go through a succession of equilibrium states, almost equilibrium states. Such a transformation is called a quasi-static transformation. Quasi-static transformation. So what it means is, this is a transformation in which the system passes through a succession of almost equilibrium states. I hope this is clear. So what I could have done instead is that, let's say the piston was here, and then I suddenly pull it out. Okay, so then of course the system will no longer be going through a succession of equilibrium states. It's like saying that you are initially in equilibrium and then you disturb it very slightly so that it goes to another equilibrium and another and another and another. The other possibility is, you suddenly pull it out and the system goes crazy. Okay, so that's not what a quasi-static transformation is. Quasi-static transformation is you don't let the gas go crazy. You say that, okay, I will disturb you little by little by, I annoy you. Okay, you must have seen people, they keep, nagging, they keep annoying you and so on. So it is of that sort. Yeah, you can use it. I'm giving an online lecture, so you can. Okay. So that's the example of a quasi-static transformation. And of course, quasi-static transformations come in two varieties. So let me just come to that. Quasi-static transformation, can say. So what are the two varieties? The two varieties are the following. So I have to draw a picture here. I will draw two pictures. The first one is, let's say, the position of piston. The function of time. And this is, let's say, the state of the system. Again, as a function of time. Okay. So, as I mentioned, suppose I move the piston very, very slowly from one position to another. So, this is the path of the piston, let's say. So, let's say I go this way. Okay. I change the, I pull out the piston according to this, this trajectory. Okay? And correspondingly, the system starts from an equilibrium state A and it goes through a succession of equilibrium states. And let's say this is the path taken by the system. So it goes from state A to state B. Each of these intermediate states is also an equilibrium state. A is an equilibrium state, B is an equilibrium state. So let's say this is the path of the system. I give this the arrow just to emphasize the fact that, I'm changing the position of the piston this way, and this is the direction in which the state of the system changes. But suppose I now do the following experiment, that I have moved the piston from this position to this, and suppose what I do is that I just have nothing to do, and therefore what I do, yeah.
Sir, in first graph, y-axis, we cannot able to see what you write.
This one?
Yes, sir.
Okay, 1 minute. This one is fine, right? This one?
Yeah, yes, fine, sir.
Okay, right. Here I am writing so position of the piston. Now it's okay? Now it's okay? So can you see this one?
Yes, sir, but in upper portion, and the entire chalk will occupy. It is not clear, sir.
This one is not clear or this one is not clear? This one is not.
Yes, sir, this one, sir.
Okay, okay. Let me see. Let me try with this one. This one is better. This one is better. Position.
Yeah, okay, sir.
Okay. position of piston. This is my time. Y-axis is the position of piston, and let's say I go from this part to that. Okay, so this is my time. This is clear, right?
Yes, sir. Clear, sir.
Okay. So what I'm saying is that I change the position of the piston from this position to that quasi-statically. That is, I change it very, very slowly. And if I do so, then this is the change in the state of the system. I go from state A to state B through a succession of equilibrium states. Okay. Now, suppose I do the following experiment that, okay, I have changed the position of the piston from position 1 to position 2. But suppose I go now in the backward direction. That is, now, instead of pulling out the piston, I push it in, but I push it in exactly the time reversed manner. Now I go from 2 to 1. So first experiment is I go from 1 to 2. The first experiment is I go from 1 to 2, and then the system went from A to B. And now I go from 2 to 1. And if it so happens that the system now goes from B to A, that is, if I go in the backward direction, the system also traverses the same path but in the backward direction. Such a transformation is called a reversible transformation. Is this clear? So first is quasi-static. Quasi-static means that I change the position of the piston so slowly in time that the system goes from one equilibrium state to another, to another, to another, to another, and so on. That's quasi-static. Next, what I'm saying, I change my piston slowly and the system goes from one equilibrium state to another. So I change the piston position from 1 to 2. The system goes from A to B. Now, if I change the position of the piston in the backward direction, I come from 2 to 1 along the same path but traverse in the reverse direction. If it so happens that in doing so, the system also traverses the same trajectory in the backward direction, I say that the transformation is reversible. Okay? So quasi-static transformations are not necessarily reversible, but reversible transformations are of course quasi-static because of this. Okay, quasi-static can be reversible or it can be irreversible. I'll come to this one in a minute. But reversible transformations are necessarily quasi-static. Okay? And okay, so this is what you call reversible. And when do you call it irreversible? You call it irreversible when you change from 2 to 1 and the system doesn't follow the same path. It goes from B to some other state C, or maybe it comes back to A but along a different path. Then you say that the transformation is not reversible, it is irreversible. Okay, so this is the definition of reversible, and if this one, if it doesn't hold, then you call it irreversible. So it's a very simple notion, but then it has important consequences in thermodynamics. But the notion is very simple. If you think of it from an experimentalist point of view, it's very simple. That I once pull out the piston very slowly, then the system goes from one state to another. Now I push in the piston and the system comes back along the same path. This is reversible. Irreversible is when I pull it out, then the system goes this way, and when I pull it in, it goes in some other direction. Like it takes up some other path. Yes. Are there questions on this reversible, irreversible, and quasi-static? So since there are none, so let me just move on. And then I need only 2 or 3 more definitions, and then we can state the laws of thermodynamics. Okay? Okay, so the next one is the concept of work and heat. Okay, so now we start talking about the following thing. That okay, I have my gas contained in this cylinder and there is a piston and so on. Okay, so now what I want to do is the following. Of course, there are gas molecules here, and I want to impart some energy to the gas molecule. Okay, I want to make them more energetic, or I want to take away some of their energy, I want to make them less energetic. So then what are the ways to do that? Okay, so one way to make them more energetic is to do some work on them. Okay, so this is this is something that we all know from everyday experience, that let's say I have to when I do some work, let's say when I push a table. Okay, so I'm doing some work because that table, when I push it, I have to do work against the friction between the table and the floor. So I'm transferring energy. Why I'm transferring energy? Because in pushing the table, I get exhausted. And energy is conserved, so therefore I get exhausted. So where does my energy go? That energy goes into the into the table. Okay, it makes the atoms and molecules at the contact point more energetic, and that is the reason why you find that at the contact point between me and the table becomes heated up. Okay, so work is one way to transfer energy to the system. So this is a way to transfer energy to the system. Transfer energy to the system. Well, I can do work on the system to transfer energy to the system, or the system can do work on me, and in doing it this way, the system will transfer energy to me. System meaning here. So one possibility is that I push the piston in, and if I push the piston in, then I am transferring energy, I am doing work. So in pushing the piston, I am doing work on the gas. Okay, and therefore I am transferring energy to the gas. The other possibility is I pull out the piston and then the gas will do work on it. Okay, so this is this is a way to transfer energy to the system by just moving the position of this piston, and then I know that work done in this case. Suppose I start with the volume V, and in pushing out the piston, the volume increases from V to V plus dV. Then the work done will be given by PdV. This I guess you know, and it's quite easy to derive. Why is it PdV? Because work is force into displacement and pressure is force per unit area. So therefore, this exactly has the right definition and right formula. Okay? I guess this I don't have to show, because this is a trivial thing to show that this is the work done by the system. Okay? But there is another way in which I can transfer energy to the system. I don't have to do any work. I don't do any work. I don't push anyone. I don't pull anyone, and yet I can transfer energy to the system. What is the other way? The other way is to turn on a source of heat here. I put this piston on a gas burner, let's say. So if I put it on a gas burner, of course the gas burner is on, and therefore there will be transfer of heat from the gas burner to, from the fire that's there to the system. Okay, so heat is another way to transfer energy to the system. So there are two ways to transfer energy. Either you do work, or you keep the system in contact with the source of heat. Okay, so these are the two ways to transfer energy to the system. Okay, I guess I don't need to do this. Okay, so now I think we are in good shape to talk about the first law of thermodynamics. Okay, so which is the following. So to understand that, let's first understand one important concept about this work done, which is when I do work on the system, as I mentioned, I am pulling out the piston, let's say, or I am pushing in the piston. So the system is initially in equilibrium, and I push in the piston or pull out the piston very slowly, so that it's a quasi-static transformation. I go from one equilibrium state to another, and this is the total work done. It turns out that this work done is a function of the precise path that the system takes in going from one equilibrium state to another. That is to say, if you recall the figure that I just drawn, and of course then like erased, that I start with state A, and then I change the position of the piston. I go from one equilibrium state to another, and I go all the way up to an equilibrium state B. And if I ask what is the net work done by the system in going from state A to state B, this would be according to this formula PdV. I have to integrate between state A and state B. But it's an experimental fact. People have found out that you may go from same point A to same point B along many different paths. Let's say in one experiment you take this path, and in another experiment the system takes this path. Okay? Because I change the piston in another manner, and the system goes from A to B along a different path, and you would say that, well, I have to do the same integral, but then it turns out the value of this integral depends on the precise path that you have taken. For example, if I call this path A and if I call this path B, then this is work done along path A, and this is not equal to the work done along path B. Okay? So you have to do the same integral, but the value of this integral doesn't depend solely on the endpoints. It depends on how the system actually evolved from state A to state B. Okay? So that is to say that work is a path-dependent quantity. And so the way to denote it is to say that this dW, the incremental work, the infinitesimal work that you do in changing the equilibrium state slightly, that is a path-dependent quantity, or more precisely, that is an inexact differential. So d bar means inexact. Well, what does it mean? Inexact differential. The meaning is exactly what I did here, that d bar W from A to B along path 1 is not equal to d bar W A to B along path 2. Okay? It's an experimental fact. You must have encountered similar thing in complex analysis when you do, or let's say, yeah, I think in complex analysis you get this. But this is an experimental fact. These people found out from doing experiments. Okay. So work is a path-dependent quantity, and it turns out that heat is also a path-dependent quantity. So work is a path-dependent quantity. So therefore, I write d bar W, and heat. See dQ. What is dQ? dQ is the amount of heat transferred to the system, the infinitesimal amount of heat transferred to the system in a thermodynamic transformation in which you perturb the equilibrium state slightly. That also is a path-dependent quantity in the same manner as this. You go from A to B, the heat that you transfer to the system depends on the precise path that the system took in going from state A to state B. Okay? So again, this is an experimental fact. You cannot ask why is it so. In thermodynamics, there is no answer for it. We understand it only when we do statistical mechanics, but in thermodynamics, these are experimental facts. As I mentioned at the beginning, thermodynamics is an experimental subject. So you cannot question why is it so. You have to just digest the facts first digest them well, and then ask why do they happen, and then you find that thermodynamics is unable to explain this. But let's first digest them. So work is a path-dependent quantity, heat is a path-dependent quantity. But it turns out that if you take the difference of the two, then magic happens. And what is that magic? So let's see what is that magic. So work is a path-dependent quantity, heat is a path-dependent quantity. This one depends on the precise path that the system takes. This one depends on the precise path that the system takes. But if you take the difference of the two, then you find that this one gives me a quantity du that is path independent. You have two path-dependent quantities. You take the reference, you get a quantity that is independent, path-independent. Okay? Is it obvious? Not at all. I mean, two path-dependent quantities, you take the difference. Why does it become path-independent? No one knows, but it's an experimental fact. People found out that this is the case. We don't understand it until we come to statistical mechanics. But at the level of thermodynamics, this is the content of the first law of thermodynamics. So let me just rewrite it in a slightly different way by bringing that guy to this. So I say D cross Q is equal to du plus d bar W. What does it say? This is the heat transferred to the system. That was our definition, right? D cross Q is the heat that I give to the system. D bar W is work done by the system. Work done by the system. So then let's look at this equation. What it says is that the heat that you give to the system, the heat that I transfer to the system, a part of it is used in doing work. Okay, so what is the part of the heat that is transferred to the system that is used in doing work? That is d bar W. And the rest of it goes into changing something of the system, and that something is called the internal energy of the system. So this is the, let me not write it there. This is the change in the, let me make some space somewhere. Here. This du, this is the change in the internal energy of the system. It has to be a change because why? I'm giving some heat to the system. So I'm transferring some energy to the system. A part of it goes into doing some work, and a part of it remains in the system. And that part that remains in the system, that is the du, that is the change in the internal energy of the system. Why is it called internal energy and not energy? Well, convention. Until we come to statistical mechanics, we will not know what is the connection between internal energy and energy. Energy, the way we understand it in classical mechanics, how are the two related, we will understand when we come to statistical mechanics. But at the level of thermodynamics, it has a very well-defined meaning, namely that work done is path-dependent, heat is path-dependent. I take the difference, I get a quantity that is path-independent, and I call it the change in the internal energy of the system. You see that, in this the way of defining things, you define only the change in the internal energy and not the internal energy, the exact value of the internal energy, the way we have defined it. Okay? So this is the content of the first law of thermodynamics. So this was a remarkable thing in the history of physics, that before first law came into existence, you had only the Newton's laws of motion, and that's it. You did not have any other law. And suddenly these people, Boyles and Gay-Lussac and Charles and so on, they did experiments and then they came up with laws of thermodynamics, laws beyond Newton's laws of motion. And these are called the laws of thermodynamics. This is the first law. It's a law, it's not a theorem. It's based on experimental facts. You cannot ask, can you prove for me the second law of thermodynamics or the first law of thermodynamics? It is as good as asking or as bad as asking, can you prove Newton's second law of motion? No, it's an experimental fact. People have done experiments over many, many years, hundreds of years, and have found that the laws are always valid. One doesn't know why. Okay? Just as here. And in statistical mechanics also, we will not explain these laws. We will just understand how to relate these quantities to the positions and the momenta of the particles making up the system. We will not explain why there is first law, why there is second law. Just as in no theory in physics can you explain why there is Newton's first law and why there is Newton's second law. These are laws. You cannot explain. So this is the content of the first law of thermodynamics. Now we move on to the second law of thermodynamics. The second law is even simpler. Up till now, any question? Okay, none. So now we come to the second law of thermodynamics. Again, it's a law, there is no proof, but second law is something that you see from experience. What is the second law? So there are many, many formulations of the second law that you can look up in books, Carson Wong or Enrico Fermi. There is Kelvin's statement and what was the other one? The Clausius' statement and so on. But basically what it means is the following, that this cannot happen, that I keep absorbing heat and transfer all of the absorbed heat into work. Okay. For example, let's say, consider this room. Okay. So this room is, it contains a very many particles, and of course, it has an amount of energy that will never get exhausted, at least in a finite time. Okay. So what I can do is that I can keep absorbing heat from the air around me and keep running, that is doing some work. Okay, this is impossible, that I keep absorbing heat and transfer all of it into work. Okay, so what is the second law of thermodynamics? It tells us that there is no thermodynamic transformation possible for which the sole effect is you absorb some heat from some source and transfer it, all of it, into work. Something else has to happen in the universe. Okay, so there is another formulation of second law of thermodynamics that tells us that you cannot transfer heat from a cold to a hot reservoir without any change anywhere else in the universe. Something else has to happen. We know that the way refrigeration happens. There has to be some mechanical process under which heat gets transferred from one reservoir from cold to hot, but naturally it will not happen without any other change in the universe. So the statement is that you cannot change, you cannot transfer heat from a cold to a hot reservoir without doing any other change in the universe. And this is something that we know from everyday experience. If I just keep absorbing heat from the environment and keep running for the rest of my life, for the rest of the time that I exist on Earth, and what is the other change that I need to do? I need to eat. I need to eat. I need to, I need to get some energy from the food that I eat. So suppose I don't do any of those things. I just keep absorbing heat from the atmosphere, and then I keep running, keep giving lectures. I don't ever get exhausted. Nothing. Whatever heat I absorb, I transfer it completely into work without doing any other change in the universe. It is impossible. I need to eat, I need to lie down, I need to take rest, I need to have other things, other like energy changes happening. That is the content of the second law of thermodynamics. And consequence of the second law of thermodynamics is what is known as a Clausius's inequality, which is the thing that we will do next. So it's a consequence of the second law of thermodynamics. It's not a proof of the second law. So what does Clausius's inequality tells me? You remember the picture that I had, that I started out with a system which is in equilibrium at state A, and then I did some thermodynamic transformation, and the system went from state A. This is quasi-static, let's say. Okay? So the system goes from one equilibrium to another, to another, to another, to another, to some state B. Okay, so this is, and suppose I do another thermodynamic transformation that brings back the system back to it. Everything is quasi-static, not necessarily reversible. Okay? Suppose I do this experiment. Then what Clausius's inequality tells me is that this is a cyclic process. Why this is cyclic? I start from A, I come back to A. That's what cycle means, right? That you start from somewhere, you go around and you come back. That's the definition of a cycle. So it's a cyclic process. And what Clausius's inequality tells me is that for this cyclic process, if I compute this guy, now we know the meaning of every symbol here. D cross Q is the amount of heat transferred, in one of these states, infinitesimal amount of heat. T is the temperature. Temperature also I know how it is, how it appears. So this quantity, what Clausius's inequality tells me is that it is less than equal to 0. This quantity, this integral, this integral computed along the cycle, it can never be a positive quantity. It can be either 0 or negative. A proof of this you will find in any standard textbooks. So I'm skipping that, but I think perhaps the best proof is given in the book by Enrico Fermi that I mentioned. Okay, but it's a very elementary proof. I mean, you can understand it in no time. But let's first understand the content of the inequality. What does it say is that if you compute this guy, you get a negative number or 0. When do I get a 0? So this one, equality, will apply if the transformation is reversible. And this inequality will apply if the transformation is irreversible. Remember that both are quasi-static. So this process is quasi-static, but it can be reversible or irreversible. If it is reversible, then you compute this quantity and you find that this is equal to 0. And if it is irreversible, you compute this quantity and you find that the quantity has a negative value. Okay? And this is a consequence of the second law of thermodynamics. If you believe in second law of thermodynamics, then one can prove that this is a mathematical equality that emerges. And for that proof, I urge you to look up any standard textbook on thermodynamics. Okay. But in this one, this inequality, it has an immediate consequence in defining a very important quantity in thermodynamics, namely the entropy. So let's just see what, how does that definition come about. But before that, again, let me pause for a minute and ask if you have questions. Okay. So no questions. So therefore, let me proceed. Suppose you have a cyclic process in which you go from A to B and then you come back to A. You go from A to B and you come back to A. And this one is reversible. The forward path, the backward part is also reversible. Everything is quasi-static, but you may have a quasi-static reversible transformation or you may have a quasi-static irreversible transformation. I am for the moment assuming or envisaging an experiment in which everything is reversible. Okay? Then Clausius's inequality tells me that V cross Q by T, I have to take the equality sign here. This is equal to 0. Okay, that's the content of the Clausius inequality. But now let us try to evaluate the left-hand side. Okay? So the left-hand side is what? The left-hand side is equal to, this is a closed thing. So what I have to do is I have to go from, let me call this path 1, call this path 2. So it says this one, I can break it up into two parts. I go from A to B along path 1, B plus Q by T, plus B to A along path 2, B plus Q by T. I hope this is fine, because this is what it means to compute this along this cycle. You evaluate it from A to B along this path and you evaluate it from B to A along this path. This is what it means. And what inequality tells me is that this guy is equal to 0. So let's just do some massaging here and see what I get out of it. Let me just, so I say A, I, B of D plus Q by D. So this is a plus sign, I take it to the other side, I get a minus sign. Minus of B to A D plus Q by D. But remember that the path 2, this path 2, this is a reversible transformation. So therefore, going from B to A and going from A to B, this will be the same, because this being a reversible one, I will get this A to B along path 2. This was the definition of a reversible transformation. That if in going from B to A, you absorb heat, in going from A to B, you give away heat, and the path that you follow is exactly the same. So that's why I can absorb this minus in the definition in this D cross Q by saying that if I had absorbed heat in going from B to A along path 2, I will give away heat along the same path if I go it in the reverse direction. But now if I look at these two sides, I have A, I, B, D cross Q by T, A1B, sorry, is equal to A, 2B, D cross Q by T. What does it say? It says that this integral A to B D cross Q by T, this integral it is independent of the path that you take from A to B. It has the same value if you take path A, path 1 or path 2. And it applies to any reversible path, okay? You may have another reversible path, path 3, or another one, path 4, and so on. For all those reversible paths, the integral is going to have the same value. Okay? So therefore, this integral, it is going to depend only on the endpoints. It does not depend on the path. It has the same status as that of the internal energy. We said that the change in the internal energy is independent of the path. In the same way, the change in this quantity, d cross q by t, it is independent of the path. Although d cross q is dependent on the path, yet d cross q by t is independent of path. So therefore, this one is an exact differential. It is no longer an inexact differential. It is an exact differential. And the function that you get here, this is called the entropy. Okay, so this is how you define entropy based on second law of thermodynamics. That if you have a reversible cyclic process, you find that d cross q by t integral is independent of the path. The reversible path that you take from to go from A to B, you will get the same values if you take this path or that path. So that allows one to define d cross q by t to be equal to a function that is independent of path, and that is called the entropy. In fact, there is a name for such functions that are independent of path. It is called the state function. The state function means what? They are path independent. So, for example, du, ds, they are path independent. And what are not state functions? These are not state functions. Heat is not a state function. Work is not a state function. So these are not state functions. So that's why you put a bar here. These are not state functions. These are state functions. They are independent of path. Independent, for example, for this entropy, for any reversible path, you'll get the same value. Okay? Achha, can somebody tell me when should I stop? Should I stop? Should I stop now or in 5 minutes, or can you tell me?
It's 11 o'clock. It's right now. It's stopped.
Okay, fine. So I hope. Okay, so let's stop and then we can reconvene at 1:30, right, or 1:25, something like that. Can you confirm to me the time?
So 1:25.
1:35. Okay. So yeah. So let me then before I move on, are there questions that you would like me to answer now? Was the lecture understandable? Did you understand everything, or I was too fast or too slow? I need some feedback, because if you feel I'm too slow, I will speed up. If you think I'm too fast, I will slow down. So tell me, like, is the pace okay?
Yes, sir. We are finding it okay, sir.
Okay. So, and the lecture is also understandable, right? I mean, whatever I talked about.
Yes, sir. It's understandable.
Okay, fine. So let me then stop the recording first, and then